Okay, so in this video we're going to look at de Moivre's proof by induction. So same set of steps as always. It'll just take a little bit longer by the nature of the proof. So we want to prove true for n equals 1. So this proof comes from the formula that we see in our log tables. So we're going to have left hand side, we'll have right hand side, and the best thing to do is just carry these down the whole way throughout. So we get r on cos theta plus I sin theta to the power of 1 will equal r to the power of 1 on cos 1 times theta plus I sin 1 times theta. Tidy up the left side. So to the power of 1 won't change anything. So then we'll get r cos theta plus I sin theta. You can drop your square brackets. R to the power of 1 gives r. 1 by theta will just give theta. And there we go. Left hand side equals right hand side. So it's true for n equals 1. Step 2 now. We're going to assume true for n equals k. So for this step here, it's just going to be some substitution. And we get r cos theta plus I sin theta to the power of k will equal r to the power of k on cos k by theta plus I sin, and same again, k by theta. We'll just tidy up. So we get r cos theta plus I sin theta to the power of k is going to equal r to the power of k on cos k of theta plus I sin k of theta. Okay, so that step now we're going to leave where it is, but we'll come back to that in step 3. We'll use it to substitute in, and then we'll be multiplying out and so on. Okay, so step 3, as always, we're going to prove true for n equals k plus 1. So again, left hand side, right hand side. We'll have r on cos theta plus I sin theta to the power of k plus 1 will equal r to the power of k plus 1 all on cos k plus 1 by theta plus I sin k plus 1 by theta. Left hand side here, using indice rules, I can rewrite, and then that'll help me introduce my assumption from n is equal to k. So we'll have r cos theta plus I sin theta to the power of k multiplied by r cos theta plus I sin theta to the power of 1, and then that equals r times k plus 1 on cos of k theta plus theta plus I sin k theta plus theta. So I've just multiplied out my brackets in that previous step, and then what happens here is we have, I've got a square bracket here. So this step here now, I'm going to rewrite. And here's my substitution. So this becomes r to the power of k on cos of k theta plus I sin k theta. That's multiplied by r cos theta plus I sine theta. You can drop your 1 there, as the 1 won't change anything for us. And then right hand side, again for indice rules, we have r to the power of k plus 1. So we can go and tidy that one up. That will help us out. Okay, so then left hand side here, we have r to the power of k and r, so I can rewrite that. Just rearrange it so they're beside each other. And now I'm going to split these brackets. So it'll be cos k theta times cos theta plus I sine theta plus I sine k theta on the same bracket. So I'm just looking to multiply out, rearrange, rewrite my left hand side so it ends up equaling the right hand side. Okay, so this r to the power k by r on, and again here a little bit of multiplying out. So we get cos k theta plus cos k theta I sine theta, and same again here, so we have I sine k theta cos theta and I squared sine k theta cos theta. It's all going to equal your right hand side. Okay, so this part here now, you'll see at the top of the screen I have pasted in a section from the log tables. So we had these two here. I'm just going to move them down. Okay, so we have these two identities from our log tables, and we see cos of a plus b will equal cos a cos b minus sin a sin b, and then sin a cos b plus, or sin a plus b, sorry, will equal sin a cos b plus cos a sin b. So what happens here is, instead of a, we have cos or k theta, and instead of b, we have theta. So we're just going to see what way we can rewrite that. So that would be cos a cos b, then we have a cos a sin b, and then here we have a sin a cos b, a sin a cos b. Now we just have to be careful in terms of putting real with real and imaginary with imaginary. So if we look here, we have imaginary, and then we know that I squared is equal to minus 1. So this here then will be the real part. So we're just going to go ahead and rewrite that. So we have r to the power k by r on cos k theta cos theta. So there's the first blue part. Second blue part I'm going to put beside it, plus I squared becomes minus 1 sine k theta cos theta, and then we get plus cos of k theta I sine theta. Actually, this one we can rewrite. If we have a look here, it's sine a cos b. So we'll put the second part first. So we get I sine k theta cos of theta, and then plus cos a sine b. There's our correct order. close your bracket, and that equals the right hand side, which has stayed the same throughout this. Okay, so here what's happening is you have cos A, cos B, that'll become a minus. We have sine A, sine B, and then here we get sine A, sine cos B, and then we have cos A, that's our plus in between, sine B. So now our log table is going to let us rewrite that. So there's my first identity, and there's my second identity. So the first one is going to tidy up to cos of A, which we said was k theta, plus B, which is theta. So there's your first part, and then the second part tidies up to sine of A, which is k theta. Let me drop the I. So I sine k theta plus B, which is theta. And then that'll equal the right hand side. So we have left hand side equals right hand side. You can put a tick, and it's true for n equals k plus 1. So now back to the original statement given in the question. So we want to prove that cos of theta plus I sine theta to the power of n equals or to the power of n cos on n theta plus and then there's your second bracket, and then for all n element of n. As we have, and here's our generic statement, proved true for n equals 1 and n equals k plus 1, assuming true for n equals k. Okay, so there's an example of the Moivres for proof by induction, and that's us done.